Hi, I'm Phil, and today we're going to do part two of the Blacktown microbit garden workshop. And here we're going to explore plant lives. So the objective is to look at light management. So this would be particularly useful in an indoor setting where you need additional artificial lights to stimulate plant growth. And we'll have a look at the measurement of light with a lux meter. And we're interested in knowing when to start and when to stop the process so that we can ensure that the plants get enough exposure to light. We can also have a look at what are the best colors used for plants. Since we'll be using LEDs, we have a selection of colors to choose from. And we'll have a look at lighting levels where we have mixtures of artificial and sunlight. And we can set light set points so that when the light levels is below a certain level, which is the set point, we can switch off the lights. Or we can turn on the lights if we satisfy this very simple algorithm. So the measured light, if it's less than the light set point, we turn on the light. And we'll also learn about how to use relays to control larger amounts of current. And in the projects we've done so far, we've only used small amounts of current. And if we use powerful lights, we will be dealing with larger currents. And we'll also compare different types of LEDs. Those which are designed specifically for plants. And we'll also compare that against the Grove neopixel LED strip. So we've already looked at photosynthesis and how the nutrients and minerals come up with the water via the roots. And we also have carbon dioxide, which enters via the pores in the leaf. So this whole process of chlorophyll and sunlight, they combine to produce the glucose and the oxygen, or the carbohydrates. So you can see the process illustrated here on this diagram. And there's the chemical equation, quite an important one for sustaining life on Earth. So we've already looked at the process of water, and now we're going to look at light. And our other objectives involve learning about programming and coding. So we'll be learning about the variables, functions, logic, digital read and digital write, and the use of timers. So what's extra here is that we'll be using more of the accessing microbit pins or ports to do write and read. And a little bit more, we'll be looking at how we can debug our program using the serial communications, and we'll be transmitting the values, not only for debugging, but we can route those values to Microsoft Excel to analyze our data. And we'll be using an array to achieve that, which will have both the measured and the set points for light. So our design will be measuring light, and we'll be remapping that so the dark value will be 0. And we're not using a calibrated light source. We're using an analog sensor. The upper values are more likely to be about the maximum value of the analog to digital converter, which is about 1024. And the maximum values that I've seen so far are around about half of that. we'll be using button A, just as we did before, to increment the set point. So we increase it by pressing button A. And when it reaches a maximum value, it just goes back to the starting point and ramps up again. We want to turn off the lights. We press button B. And if we just want to test the lights, we press a combination of button A and B together. And if you press the logo button, you turn off the electrical power. We also want to be careful that the maximum current limits are not exceeded. So on the diagram here, you can see a plant LED strip, and that actually uses quite a lot of current, a lot more than what the microbit is capable of supporting. So the hardware will be using microbit, bitmaker, cables, and we'll be using a Grove light sensor and also a Grove relay. And just look at the rated load on that, 5 amps. And finally, that relay will control an LED growth light flower lamp. So you can see the pictures of all those. All we have to do is put them together. And one of the things that we'll be working on is try to understand how a relay works. So as we've seen, the microbit is only capable of delivering a maximum current of 110 milliamps. And yet we'll be working with currents in the order of about 2 or 3 amps. So there's just not enough current that can be provided by either the microbit or the bit maker. And this is a diagram of how a relay works. So you can see on the bottom there, which is colored in orange, we have a coil, and there's a magnetic component there, which when we turn on the power, it trips the armature, and we then close the air gap and complete the circuit. So it's just like a switch, which is easier to see on the next diagram. So on the left, we have our primary circuit, and there's the microbit supplying current to our coil. And the microbit actually is able to turn on and turn off that switch. So it's not just a manual switch, it's controlled by the microbit. And the relay, once that coil is energized, then closes the contacts of the relay, and the secondary circuit allows current to then go through the load, which in our case will be LED lamps. And the extra components, we need a Windows PC with power and a USB adapter with 2 ports. One of them will go into BitMaker, and the other one will go into the LED lamps. We need USB cables and a USB extension cable. So how does it all connect together? Well, we start off with microbit and our PC with 2 USB cables, one going into microbit and the other going into BitMaker. So on the bottom there, we've got BitMaker, and we're connecting the Grove light sensor to port 0. And to port 16, we connect using another Grove cable to the Grove relay. And there are a couple of contacts on that Grove relay. So if you look at the little block in green, that's where we connect our secondary circuit. And here it is. So we're completing the circuit where we're using USB adapters that can tap into the USB power, and we're switching those on and off with the Grove relay. So if you had enough time, we'd actually get you to wire that circuit up and you can get a little bit of experience on the physical side of a STEM project. And we plug in our garden LEDs onto the USB adapter. Safety first. If you find that the LEDs are too bright, just turn them around and let them face the table. We're only going to use USB power. There'll be no AC or 220-volt power used in the project, other than powering the computer and the USB adapters. And make sure you have packed away all the components that we used previously for water, and there's no water around, so we don't want to spill water onto the desktop. Okay, so here's our project, and we'll actually just walk through that just to make sure you are happy with it. And you can then copy it and get it to work on your project. So on the startup, we're setting up the variables and we're giving the program a name. And some of those variables involve the light SP, or the light set point. So we're establishing that at 200. Remember, the total range here I've got goes from 500 to 1,000. So perhaps if we want to increment, we start off at 500 and just then build up towards our light set point maximum. And we've got a couple of flags there. One is for the light testing and the other one's for light stopping. We're not using the forever. As an alternative, we're using an interrupt every 1 second. And when that happens, we then call 3 functions. The first one is to get the data, check the light values, then transmit the data to the Windows PC by the USB communications. When we press button A, we then increment the light set point. And if that's at the maximum, we reset it to the minimum and we plot that value onto the microbit LED array. Then we just wait a second and we can repeat that. Button B is just simply a toggle where we can, if it's stopped, we can set it to true or vice versa. We press both A and B together. We're turning off the relay, or we can turn it on. So it's like a toggle where we can perform a test on our light. So how do we write the pins? Well, in the toolbox, we add one of the advanced features where we can see here that we can do a digital pin write, and the pin that we're interested in, because our grow relay is connected to it, is pin 16. And to get the data, we just simply read from port 0, and that's where our light sensor is connected. And when we do that, we plot the value and we make sure that it's within range where the maximum is the light set point maximum. Here we're checking the light, and if the light, you can see from the algorithm, if the light is, as it's measured, is less than the set point, we turn on the relay, otherwise we turn it off. And here we're just transmitting the data on the USB serial line. And once you've coded it and you think it's going to work, download it and test it. Okay, so did it work? And what was the value of the light intensity? So there's a light meter on hand, so you can actually compare when the relay is on, what the light level is compared to the ambient lighting, and you can see what contribution that this light strip is making. And were you able to start and stop the light? And did the algorithm work? So you can cover up the light sensor. And if you do that, the light LED or plants should turn on. Okay, here's something different. This time we'll use a different arrangement. So instead of a special strip just for lights, we're going to use the neopixel strip that comes with the BitGadget kit. So the similar objectives, the same algorithm as we had before. And right at the end, you can compare the values of the light that you get from it. The only difference here is that we can actually control the light color using this setup. Okay, so similar to before, we're going to use the Grove light sensor, but instead of the relay, we're going to connect the Grove neopixel strip with its Grove plug. And here's the complete code for it. And we'll go through that. On the startup, similar to before, we've added an additional function here, which is setting up the strips. But otherwise, it's the same as we had before. So let's have a look at that one. Setting up the strips allows us to configure port 16 with 30 LEDs. And we're going to create substrips from strip 1 to strip 10. And each of them has 3 LEDs. And we're going to configure those with the right colors later on. So similar to the previous program, every 1 second, we call 3 functions: get data, check light, and transmit data. And this is exactly the same as before. And similar with button B and button A and B. But here, when we turn on the lights, it's a slightly different routine that we're using. So we call the turn LED on or off, depending on the value of the light test flag. Same as before, to measure the light value. And this is also the same, except when we want to clear the light, if we want to stop it, we use a neopixel command. And to turn on the LEDs, we're going to use alternative combinations of red and blue. So strip 1 is going to be red, strip 2. So all of the odd numbers are going to be red and the even numbers are going to be blue. And we'll be using all 30 LEDs subdivided into 10 substrips. And to turn off all the LEDs, we just simply use the black color for all of those strips. To transmit it this time, we're going to transmit an array of measured light, the set point, and also the flag of the light stop number. So you might like to code that up and download it to your microbit and see if it works with your Grove neopixel LED. So did it work? And what were the lux measurements this time? How did they compare with the previous configuration? And quite interesting, you can actually go a little bit further here and have a look at the values and feed them in to Microsoft Excel on your PC and collect and analyze that in real time. Okay, so this is what it might look like if you were to use the plotting function on MakeCode. You'll be able to pick up all those variables. Okay, as an extension to this, you might like to use light intensity instead of the maximum light exposure. So here we're going to use exposure instead of light intensity. And I'll leave it up to you to go through this. So this is our final project. And if you had enough time, you'd be able to complete that. Okay, so here are some of the references. The mind maps that I've used for the environmental topics, including light, water, air quality, are here. And there are plenty of references on the internet. One of the most interesting ones is from Columbia University on the state of the planet on how climate change will affect plants. So you might like to go ahead and have a look at that particular site, and it will tell you also about the impact of carbon dioxide, the increase of carbon dioxide on the photosynthesis process. And will that lead to more plant production or not? Okay, so we'll leave it there. And that concludes our videos on the microbit in the garden. This is a modification of Project 4, where we're looking at controlling plant LEDs. And what we have is an additional LED just to help with the debugging. Otherwise, it's similar to Project 4 that you have. What else we have is a light sensor, and that feeds into port 0 on BitMaker and to microbit also on port 0. In addition, on port 16 over here, we have a connection to a relay which switches on the contacts for a USB-powered plant LED light. So this has already been preloaded with software, and what I'm going to do is just demonstrate it. So when I toggle port or button B, I enable the light control. So light control is now on, and if I cover up the light sensor on the back over here, the plant LED light should come on. So I might just go, I'll have a look at that over here. There we go, we've got the light coming on. When I remove it, the light will go off. So there's our light control. And in the next configuration, we're going to use neopixels instead of the plant LED array. Now we have Project 5, and we're using the neopixel strip, which is in the BitGadget kit. And what we're going to do is turn on the LED when it's low light. So we have a light sensor, similar to Project 5, going into port 0, and we've got the neopixel array going into port 16. Now, be a bit careful. If you've got version 2 of the BitMaker, they've swapped port 15 and port 16. And it took me a while to work that out, but that was a bit of an issue with the quality control from Seed Studio. Okay, so we're ready to go. The program has been preloaded. And if I cover up the sensor, you can see that the LEDs are on with the alternating substrips of red and blue. And if I remove my fingers, the lights will go off.